Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called binary tree zigzag label order traversal. So this is the problem that's pretty much similar to the label order traversal, right? So it says the label order traversal and it's a zigzag. So we will just try to understand what the zigzag means. So zigzag means like it's from left to right and then right to left, right? So let's try to understand from the whiteboard and from this example. Okay, so 3 9 20. So 3 is having left child, right child, and 20 is again having 15 and 7 left and right. All right, so if simply I calculate the level order traversal, basically this is first level, this is second level, and this is third level. So in simple terms, what I would do, 3, right? So 3 is at the first level, right? At the second level, basically 9 and 20, and at the third level 15 and 7. So this would be the label order traversal. But now it's saying zigzag label order traversal. So zigzag means basically we have to alternate our direction, right? So first of all we will go from left to right, and then from left to right what we will do, we will go again from right to left, and right to left again we will go left to right. So basically we will be flipping the directions alternatively, right? So let's go ahead and do that. So at the first level, what is there, and let me change the color here real quick. So first is 3. All right, second is because we covered left to right, now we need to cover right to left, so it would be 20 comma 9. All right, at the third level we will again flip the direction and we will again move from left to right, so it would be 15 comma 7, right? So it's 3, 29 and 15 comma 7. So this would be the zigzag label order traversal. So let's verify 3, 29, 15, 7. So this is the problem. Okay, now let me make another binary tree here just to move forward. So 20 and then 15 and then 7. All right, so this is the given binary tree. All right, so now we understood what is the label order traversal. Now we understand what is the zigzag label order traversal. Now let's jump to the solution part, how we are going to solve this problem. So even before jumping to the solution part, let's take the step back and let's try to think about the label order part. So when we think about the label order part, it means that we are going level by level, means we have to store these nodes at every level. So what every level means, like if we draw like this kind of boxes, then these boxes represent as a list, right? In another words, we can say these are the queues, right? So they look like as a queue, so here we can use the queue. That's one thing. Another thing is basically, again, if we go back to our basics, basically whether it will be the depth first or breadth first. So definitely it's not going to be the depth first. Why it's not going to be depth first? Because we are not going to traverse in one direction deeply and then coming back, right? So there is no such ask in this problem, right? There is no such requirement or ask in this problem. So we are definitely not going to follow depth first strategy in this problem. Rather, what we would do, we would follow the breadth first. And why we are going to follow the breadth first? The reason behind that is because we have to go level by level. So what we will do, we will just start from the root and then we will go to the second level. How we will go to the second level? So here the second level means they are the neighbors of the root. So that's why we will just traverse all the neighbors of the root, right? Once that traversal is done, one traversal is done, then we will hold all these nodes at the second level, and then we will traverse again the neighbors of these nodes, right? So that's how we are just going one step by one step each level, and we are just keep traversing the neighbors. So that's how this breadth first strategy is playing the role in this problem, right? In this problem solution. All right, so I think this is at high level, this is clear, right? So now let's quickly jump and then let me shorten this binary tree so that I would have little bit space so that we can just see that how it's going to work. All right, so let's say 3 and this is queue, right? So we would store 3 in our queue, or in fact this is queue 3. All right, so 3 we will pull from the queue. Now what we will do, we will make another linked list or queue, and then what we will do, we will insert 3 9 comma 20, right? So 9 and then 20, right, left and right. And 3 what we will do, we have another main list, right? So main list is basically we will just insert 3 in that main list. All right, now we inserted 9 and 20. We will poll 9. There is no left and right of 9, so we are not going to insert anything further, right? For 20, once we will poll 20, we will insert 15 comma 7 to this to the queue, right? And don't get confused because different queues, what here I'm going to do, I'm taking the different queues, the sublists means the local list, so that it would be really easy for to make our local lists. So these local lists we are going to add to the main list, right? So again 920, once we traverse, what we will do, 9 comma 20 we will just add to this main list, right? So this is again the local list, and this is also the local list 3. Okay, so 3 local list is having only single element, but it can have multi, because it's a root, so root will be only single, so it makes sense it will have only one element. But further 9 and 20 we can see it's 2 elements, right? So it can be any elements, right, further in the further levels after root. All right, so now we are having 15 and 7. So 15 we will poll. We are not going to insert anything because there is no left and right of 15, and 7 is also leaf level, at the leaf level. So we are not going to insert further, right? So 15 comma 7, that's also what we will do. We will insert here 15 comma 7 as a list to the last box of the main list. So that's what we are going to do. So this is simply breadth first search template. So let's do this. Let's quickly try to code the similar way. Let's take first of all our result list. So list of integer, and then result new link list, and root equals to null, then return result. All right, now let's take the queue, and uh, let's take initially the tree node because we are going to store the node itself. So let's go ahead and take that, right? So queue equals to new linked list. All right, so now initially what we would do, we would just go ahead and insert our root to the queue. Now let's go ahead and check if queue is not empty, right? And if queue is not empty, then we will just go ahead and pull from the queue. All right, and even before that, let's go ahead and calculate the size of queue, right? So let's say this is the size. Then what we are going to do, I is less than size I plus plus, and then we are going ahead and polling from the queue, right? Now let's go ahead and check if node dot left is not equals to null. Then what we will do, we will just go ahead and offer the left child to the queue, right? That's what we will do. Similarly, we will do the same thing for the right side. So let's go ahead and do that as well. Node dot right here. Okay, and now we need list of list, right? So we already have the list of list. Now what we were doing here, we were just making the local list, right? So that's what we were doing. So let's go ahead and do that as well. Let's create the local list of integer. This list is a local list, right? So linked list. Once we created this local list, then what we can do, we can just simply list dot add this node dot val. right? So because this is the integer, and after going through this one level by level, then once this local list is getting populated, we are just adding to the master list. So 3 is adding here, 920 is getting added here, and 157 is getting added here in the master list. So let's go ahead and do that. So master list is res, and then add our list. So what we did here, this is simply uh, we did not even talk about the zigzag or anything. This is just simply the label order traversal code. So let's see the compilation error, or if there is any typo that I did. If there is not anything, then just check. This is the label order traversal, right? So 3, 9, 20, and 15, 7. So there is no zigzag. There is no flipping happening right now. All right. So this was the simple thing. Now for the flipping, we can do the simple thing here. What we can do for the flipping, let's come back again here to the whiteboard. For the flipping, what we can do, we can just take another boolean flag, and with the help of that boolean flag, we can just toggle that value of the boolean flag true or false, right? So initially, let's say it is false, because default value of any boolean flag will be false, right? So initially if it is false, and then once it traverses the root node, then on the second level, what we can do, we can just flip that boolean flag value, right? So let's say it was false earlier, and then we toggled, and now it is true, right? So if it is true, then what we can do, we can just append to the list from the last, right? So once 20 is coming, then we can, what we can do, so let me use the different color here, let's say blue maybe, and here I'm just doing the toggling thing, right? So 3, and for the 3, after 3, what we are going to do here, 9. So 9 came, 9, let's say I inserted in this list, right? And then 20 came, right? So 20, what we can do, once 20 came, we can just insert in front of 9, right? So 20 and then 9. All right. Similarly 15 and 7 came, and 15 and 7 basically, because here the flag value was false, right? And here flag value was true. Again we will toggle, so this flag value would still be false. So once if it is false, then what we are going to do, it's still 15 and comma 7, right? So that's how we will be doing. If still it's not clear, let's go ahead and just do the same thing here. So let's say boolean, and let's say zigzag maybe, okay, or better naming convention is zigzag. So let's say initially this is false, and if it is false, then let's check here if this is false, if is zigzag. If it is false, false means what I need to do, I need to do not, so that it can become true. All right, so once this guy is false, false means true, then what we are going to do, we are just simply adding it, right? And if it is means we toggled the value, then what we will do, we will just next time we will do 0 comma 0, means whenever the next value would be coming, we are just adding first of all 9, and then again the value we are just adding in front of 9. So 0 means the remaining value we will be adding in the front of the last value. So that's what we are doing. If it is toggled, right? Toggled means if it is true, right? So if it is false, then it's simply nothing, like this is the normal flow. And if it is not false, right, if it is false, then it will come here, means it will be true. And if it is not false, means we already toggled, right? So toggled means it is the different direction, right to left. So just to make sure, left to right here, and this would be basically right to left. So here we are doing the same thing again, we are taking from the level, but just keep this thing in the mind, we are just doing first of all 9 0 at the 0th position, then again we got the 20, then 20 also we are just doing at the 0th position, right? So 0th position means we are just appending, not appending exactly, but we are inserting at the 0th location. So in this way we are just reversing this list, right? So that's how we are doing it here. Okay, so it is little bit convenient to do that, doing the reverse part. All right, now this is the time that we want to toggle the flag, right? toggle the boolean flag. So is zigzag equals to not is zigzag, and that's it. That we should be done here. So in the looping part, once we will just one I mean whenever the queue size, whatever the queue size is there, we are going in one direction. So for every level we are following one direction only. Let's say for example, for the root we are going left to right. For the next level we are going right to left, because now now our this toggle part has been revert it has been toggled, right? So earlier it was false, now we have the true, right? So once it will come here, right, and it will see true, and we are doing the not, so now it's false, so it's not going to come in the if part, but it will go to the else part. So every time it will be appending in the front of the list, so that's what it will do. So 9, and then again it will in the same loop 20 as well. So this for loop is covering basically each for loop, every time this for loop is covering for the whole level itself. So this for loop is basically for 9 and 20, and then again we toggled after for loop, and then it's again covering the this third level here, 15 and 7. So no matter what, how complex the binary tree is there, what is there, this implementation should be same, the idea and concept should be same, so this should work. Now let's quickly check what's going on behind the scene and whether it's okay. So looks like this is matching our output. Let's quickly for the time complexity and space complexity. So TC means here the time complexity, it is little shorter, don't get confused with the TC and SC. TC means time complexity, so I would say this is order of n, and where are the number of nodes. Space complexity still I would say in the worst case it would be the order of n. Let's compare. If the binary tree is the flat n, means it is the it is looks like a linked list, right? So it is having the flattened binary tree where we don't have any choice, but we have to go through basically we have to insert each and every node, right? So it will be the number of nodes n itself. So space complexity would also be order of n, and then time complexity would also be the n, because we are going each and every node. And space complexity, let's say if it is not a flattened binary tree, it is a binary tree, balanced binary tree, or it is binary tree like this, then whatever the maximum size of the queue would be there, that will be the space complexity. But it will be basically in that case, if the binary tree is not like a linked list, it is a full binary it is the whole binary tree, right? So I don't want to rubber stamp like full or complete binary tree, I don't want to use those terms. But if it is not flattened binary tree like linked list, then generally in the leaf level we will have more nodes in comparison of the previous levels, so that will dominate our space complexity. So in that case what will happen, whenever we will hit the maximum number of the nodes at the bottom level or the leaf level, that would have the space complexity. That will be the maximum number of the nodes would have the space complexity. So this is just quick idea, like the flavor of the different kind of the binary tree can happen, right, in the different situation. But overall approx complexity would be the linear, like so order of n for space complexity, order of n for the time complexity. I hope let's say I did not I think submit this. Let's quickly check if it is going to work. Okay, so looks like this is working fine, so we should be good. Hopefully this is useful. Thanks a lot, have a good one, bye.